Hello, welcome to today's video where what we're doing is fairly clear just from the title alone. We're basically doing binomial expansion questions where you do need to do some partial fractions to help you find the full expansion. However, the best way to explain this stuff is just to do an example. So here is an example of what we might be looking at. We've got some brackets and then a couple of other brackets with powers, and we need to find the expansion for this stuff up to including the x squared term. Now the interesting thing is though, if you look at this, you might think that this looks quite similar to some of the other problems we're dealing with in some of my previous binary expansion videos, and you would be right, because we did deal with situations where we had some brackets being multiplied by some other expansions. So you could try that approach here as well, or that's what it appears at first, because we could do the quadratic that we've got at the front, multiplied by the expansion for 1 minus 2x to the power minus 1, up to and including the x squared term, which would get you this. I know I haven't shown the working for that, but that's because we're going to be looking at this stuff more later. And then you could multiply that also by then the expansion for 5 plus x to the power minus 2 as well, which up to and including the x squared term looks like this. And then all you'd have to do is just multiply all the brackets and you would get the correct answer in the end. However, there is a problem with this, which is although it will work, it's an absolute chore to do that because you're going to have a lot of brackets to have to be manually multiplying out and then gathering like terms, etc, etc. And this was only if we were doing it up to and including the x squared term. If you were doing this up to and including the x cubed term, the x to the 4 term, whatever, it would become even more of a chore very, very quickly. So therefore, we're not going to do that, or at least that's not what I recommend. And instead, this is a prime example of a question where we'd want to use partial fractions. So therefore, how are you meant to know that you're meant to be doing partial fractions? These are the clues you're meant to be looking out for. The first clue would be that they might have, in a previous part of that same question, already made you put something into partial fractions. And just from an exam technique point of view, you should always be questioning, oh, I wonder why they made me do that previous part as part of the same big question if it isn't going to be related to what we're doing in the later parts. They would just make it a completely separate question if it had nothing to do with it. So obviously take the hint if they do that. Another thing they could do though is it depends on how they've written the thing we're looking at. If they've written it as a fraction rather than just as brackets with powers, and therefore we've got these brackets appearing as factors on the denominator, that's exactly the sort of scenario we used to deal with when finding partial fractions. So they're trying to give you a hint that partial fractions are useful. That's also a similar scenario that you sometimes come across in integration. Well, again, they'll write the fraction in this particular way, and then you're like, oh, wait a minute, that is the sort of format they often write if they're trying to hint that partial fractions are useful. But then the third sort of situation, because you'll notice, of course, in our example, we didn't have it written as a fraction, you're basically looking for the binomial expansions to only be things that have powers specifically of -1 or -2. If they're written just normally, or if they're appearing on the denominator, then just power of 1 or power of 2. Because it's worth pointing out partial fractions doesn't work really with, square roots and stuff like that. So therefore, we won't have to deal with that sort of strategy if that's what we've got in it. But if we've only got powers of -1 and -2, that is exactly what we're used to dealing with for partial fractions. So therefore, partial fractions is a good idea. Which, as you'll notice, is exactly what we've got going on here, because we've got that power -1 and we've got that power -2. So therefore, yes, that's what I know. Partial fractions is what I should be using here. Another way you could do it is when you rewrite it. Another way of rewriting this expression would then, again, make that more clear, because it shows, as I said, that sort of more traditional partial fractions structure to a fraction. So we've got 5 plus x all squared there like that. So yes, this is going to be partial fractions, and we're going to split it into the partial fractions of a over 1 minus 2x, and then we've got a repeated factor for the other thing that's on the denominator. So a reminder, repeated factors have to be split into both the repeated factor itself, written as a repeated factor, but then also that thing with just a power of 1 as the denominator. Cool. And then we've got to create the equation that will help us find the value of a, b, and c. So to do that, we need to recreate in these three partial fractions the original denominator of the original fraction. So therefore, 1 minus 2x is needing to be multiplied by 5 plus x all squared in order to create that denominator of 1 minus 2x times by 5 plus x all squared. The fraction with the numerator of b already has a 5 plus x all squared, so it only needs an extra 1 minus 2x to make it have the required denominator. And then the c partial fraction already has just a 5 plus x to the power of 1. That means we need an extra 5 plus x to be multiplied by it to create that 5 plus x to the power of 2, and also the 1 minus 2x. Cool, because doing all that creates your common denominator of 1 minus 2x. 5 plus x all squared. So therefore, that's good because it means we can compare that to the original fraction, meaning we have, of course, got our equation of basically the top of that fraction we've written is equal to 7x squared plus 64x plus 178. Cool. Now, lots of different ways of finding partial fractions, so use whatever method you like to do. I like to do the what's sometimes called the cover-up method or the elimination method, plugging in specific values of x that then make the equation really easy to find. So for instance, if you plug in x equals minus 5, conveniently that means we will have 5 take away 5 all squared lots of a, but 5 take away 5 is 0, so we get nothing. We get b lots of 1 take away 2 lots of minus 5, so therefore that's going to be 1 minus 2 lots of minus 5 lots of b. And then c, that's also going to become 0, so therefore I don't need to do anything with that. So therefore that's going to equal 7 lots of minus 5 all squared plus 64 lots of minus 5 plus 178. So therefore that will get me on the right hand side 11b. And then on the right we will get 33. So therefore we know that b is equal to 3. We could then also plug in x equals half, because that will make all the brackets that have 1 minus 2x inside just also become 0. So that means the c and the b terms are going to disappear again, but then that leaves the a term. So we're going to have 5 plus a half all squared lots of a is equal to 7 lots of a half all squared plus 64 lots of a half plus 178, and therefore 5 plus half is 11 over 2, so we've got 11 over 2 all squared, lots of a, and then working out the stuff on the right, you will get 847 over 4. Nice, so that means then when you start solving all that sort of stuff, you can obviously square the 11 over 2, which gets you 121 over 4, a equals 847 over 4, and solving that will get you a equals 7. Cool. We now just need to find the value of c, and to do that we can now choose any x value we like in the whole world. I'm going to choose x equals 0, and then plug that into both sides along with our value of a and b, and therefore we get a lots of 5 plus 0 all squared, so that's 5 squared. And then we get b, lots of, would have 1 take away 0, so that's just 1. And then we've got 5 plus 0 is 5 times by 1, so that's 5 lots of c. And on the right hand side, plugging 0 into there, that's why I picked 0, makes it easier, get 178. So therefore, 5 squared is 25, lots of a, but a was equal to 7, so 25 times by 7. We've got our b, which is equal to 3, and then we've got 5c. But then the interesting thing is that 25 times by 7 plus 3 is 178. So therefore, 178 plus 5c equals 178, so therefore c is equal to 0. So therefore we can now take our value of b, a, and c and plug them into that structure we had up here for the partial fractions, meaning because actually c is equal to 0, that third partial fraction isn't even there, so we're just going to be left with these partial fractions here and here. So therefore, we are now just having to find the binomial expansion for this expression that we've got here, which is now a lot easier than what we had before, because we're not going to have to ever multiply two binomial expansions together. We're only going to have to find two binomial expansions and then add them, which is a lot less effort. So therefore, this is the same as finding 7 lots of 1 minus 2x to the power minus 1 plus 3 lots of the expansion of 5 plus x to the power of minus 2. Okay then, so let's get on with it. This is of course just the stuff we are used to seeing by now. So the first thing to bear in mind is that the 7 lots of 1 minus 2x to the power minus 1 can just be found straight up as it is, but the 5 plus x to the power minus 2 can't be, because we've got a 5 inside the expansion and we need a 1. So therefore we're going to factorize the 5 out of both 5 and x, which will leave you with 1 plus x over 5. But that's still inside the big brackets to the power minus 2, because that then means we then need to realize that we got to take that 5 to the power of minus 2. So it's 3 times by 5 to the power of minus 2 times by our expansion of 1 plus x over 5 to the power of minus 2. Cool, so therefore we can now actually start finding those expansions. So therefore we're going to have 7 lots of 1 plus n times by x, so our n is minus 1. Our x is not an x, it's a minus 2x, so that's what we're going to write there. Then we have n times by n minus 1, all divided by 2, lots of our x term, which is minus 2x, all squared, and that is that binomial expansion up to and including the x squared term. Then we're going to have the constant out the front of 3 times by 5 to the power minus 2, which is 3 out of 25, or 3 over 25 I should say, and then the expansion will be our 1 plus n times by x, so that's minus 2 times by x over 5, and then we have our n times by n minus 1, all divided by 2, lots of our x term, all squared, like that, and so therefore that's our second expansion done. Cool, we just have to follow through basically with all of that stuff. So funny enough, that is how I got that expansion I said earlier of 1 plus 2x plus 4x squared, because you do have to remember, of course, that you're meant to do the minus 2 also being squared, because it's inside those brackets to the squared. So remember that index law there. And then we have 3 over 25, lots of 1 minus 2/5 x plus 3 over 25, lots of x squared. Again, x over 5 all squared, that bit on the end, becomes x squared over 25. So that combines with that n minus 1 over 2 coefficient to get 3 over 25. Okay then, that's all well and good, but therefore then what we need to do is then just multiply the brackets and combine everything as is relevant. So therefore, we've got that for the first brackets being expanded. The second brackets being expanded, not so nice. We're going to get 3 over 25 minus 6 over 125x, and then lastly, plus 9 over 625x squared. So, gathering everything together, we're going to get 178 over 25. We're going to get 14 minus 6 over 125, which is 1,744 over 125. Lots of x. And then combine the x squared terms, we end up with the absolutely delightful number of 17,509 over 625. Big numbers. That's how many x squareds we've got. And there we go. That would be the expansion. Now, some of you might be looking at this going, did this really take any less effort than just doing the method we said at the beginning? Well, the thing to bear in mind, as I said, this was the x squared term. It gets more and more of a time-saving method if they're trying to ask you to higher and higher expansions. And then also the other method, bear in mind, I did when I was initially looking at it, kind of skip over all these steps we're doing finding expansions. You would still have to do all this stuff that we're doing on this second slide pretty much with that other method as well. So the only extra bit really was the partial fractions bit, and that's still arguably much quicker and easier to do than doing all that multiplying out brackets that you would otherwise have to do. The other thing to point out is having to decide the domain of validity for this particular binomial expansion. The question didn't ask for it, but it doesn't hurt to write it down. And this goes back to something I did say in the previous videos, and this is why, again, the partial fractions way of writing it out is actually more beneficial for being able to see what's happening to that domain of valid values, because we know the domain of 1 minus 2x to the power of minus 1 is going to be us replacing the x with minus 2x in the inequality of x is between 1 and minus 1, which then gets us the inequality x is between a half and minus a half, or modulus of x is less than a half is the other way you could write that. But then separately, the 5 plus x interval would end up being x is between 5 and minus 5. But therefore, what you're having to think about is, where do these two intervals overlap? So therefore, the only values of x that work in both of those intervals is just the values of x between a half and minus a half. That's where those two intervals intersect. Cool, so that would be the domain of validity for this particular expansion. Of course, as I said, you could rewrite that as modulus of x is less than a half. Okay, that is all I wanted to cover in this video. Hopefully you found that useful. See you in a future video. That is the end of what I wanted to cover with the binomial expansion topic. So there you go. Goodbye.